Hello, and welcome to another creative coding video. This is the last in this short series introducing ray tracing. The first video we really focused on how to mathematically model an object. We focused on a sphere, and spheres are actually quite easy to model, it turns out. We also modelled moving light rays as they moved in a scene, and the crucial point there was being able to test whether a light ray hit an object, and if it did, we would colour it black, for example, just to kind of render the intersection, and that worked really well. In later videos we progressed on to thinking about how to shade those objects according to how well illuminated they are by the light source, and again that worked really well, and we came up with images of spheres that really did look 3D. In the last video we extended our code to work with multiple objects in a scene, and the crucial thing there was being able to do it so that objects that are more in the foreground are rendered in the foreground, and that's the thing that we wanted to get right, and we did. In this final video we're going to look at reflection. Now reflection is something we've been looking forward to because it allows us to create images, render scenes which do look quite interesting and fairly sophisticated, even though the idea is relatively simple in some sense. You'll remember also the reason why we model our scenes by not starting light rays at the light source, because that's inefficient. The light rays go in all sorts of directions, and most of them don't end up interacting with the objects and hitting the eye or camera. We send out rays from the camera or the eye into the scene. But just for a moment, let's think a little bit about how the physics or how nature works in terms of reflections. So here is the light source. Here are three spheres in this scene, and if you imagine light coming from this light source hitting the first object, it can bounce and hit the second object, it can bounce and hit the third object, and if we're lucky it'll end up in the camera, in the eye. Many rays won't follow that path and they'll bounce and go off elsewhere, but this one does, and the colour we see will be mostly the colour of this object, this sphere. It'll also include some of the colour from this sphere and this sphere as well, and what that tells us is that as we model this light ray, we're not just testing for intersection. We're not just colouring according to the first object that we hit. We need to somehow pass along information about all the objects that we've hit. That kind of suggests that we need to think about how we pass along that information. There might be two objects in the scene, there might be many more, or the light ray might bounce between two objects quite a lot, and we need to somehow collect that information. And that kind of suggests a recursive approach to the light ray. Let's think about what that means. So if we cast a ray into the scene, previously we tested for intersection, and then we thought about is that point on the object well illuminated or not, and that decided the colour, or a lighting factor that adjusted the colour. We might even think about material in terms of matte or not smooth, or even other schemes for texturing the surface, and we'll have a go at that later. But that's just the first object that we've hit. We need to bounce that ray off the first object like we do here. So we cast our ray, hits this object, and then we bounce it again, and if that ray hits another object, we do the same thing. We first obviously test for intersection, and then we kind of think about the illumination and collecting the colour information from that second object, and then we cast the ray again, bouncing it from the second object, and if we're lucky, it might be the case that it hits another object. We test for intersection and we collect more information about whether that point that it hit on the third object is well illuminated or not. So we can keep doing this, but we can't do it forever, otherwise our code will never finish. So we decide on a maximum number of reflections or depth. Do we stop after the first reflection? Do we stop after 3? And we can experiment with different values for that depth. Here I've just shown 3. And what we do is we pass backwards for this ray function the colour that's picked up. So when we've reached this third object, we pass the colour back to the ray that was cast. So the ray function itself calls the ray function, and the return value must include not just whether it's a hit or not, but the colour contribution, and that is passed back to the previous call and back again. And you'll remember this is how recursion can work. Have a look at the earlier videos that introduce this idea of recursion, which is not just about a function calling itself to do things, perhaps at a different scale, but the values that can be passed back are passed back to the calling function. So if a ray function calls itself for the second depth, it can call itself for the third depth, and the third call returns back to the second call, which returns back to the first call. And let's look at what that means visually. So this is the first ray, and that ray function itself calls the ray function, which itself calls a ray function. The colour that's picked up is returned back through the calls. Recursion can seem difficult when you first look at it, so I do recommend exploring the other video, the other tutorial on recursion, because it really explains it from scratch in an unhurried way, and it's really a necessary thing to understand before we continue here. Great. So let's get cracking in terms of coding that idea. This is the I'm logged into Open Processing as usual. I've got my simple.js library switched on as usual. This is the code that we developed last time, and I'm going to build on that. What I have done is made a few small changes. I've moved the camera back a little bit so it's further back out of the scene. I now have 5 objects of various colours because I want to see reflections of one object in another. And if you have a few objects, then we can really explore whether recursion's working or not. I've also lightened the background sky colour. Where is it? I've just added some. So those used to be 50, 50 and 100, I think it was. I've just lightened it a bit. So let's see what this looks like before we add any new code to do reflection. Great, so we have a simple scene with 5 objects, different colours, and I'm hoping to be able to now start modelling reflection and being able to see some of these objects in the other objects. So let's think about how we might do that. Okay, so let's have a look at our code to see how we might need to change it. So we're still working through all of our pixels in the viewport, just as before. We're working out our actual position in the scene from those pixels. We're still wanting to calculate a ray direction for shooting a ray into the scene, and we normalize it. The rest of this code I think we could comment out for now, because I think we can do that in the ray function, the recursive function. So for now I'm going to comment that out, this code about testing whether something is in front of another object and working out the lighting factors, because it's the recursive function which now has to give us back the contribution, the color contribution. So it makes sense to do that there. This is the pixel loop, so I'm going to comment it out up to there. So we're still doing the pixels, but everything else is commented out for now. Just going to clear our kind of code a little bit. So once we've worked out the ray direction, we need to set off the recursive ray. So set off recursive ray. And if we remember, it gives us a boolean for hit, yes or no, and gives us a red, green, blue value. And we'll call it recursive ray now. Recursive, so that if we read our code again in future, it's clear what kind of function that is. And we start with the camera location. We have a ray direction, and just following our discussion around the number of times we want it to call itself, it can't be forever, so we have to pass a number so we can keep account of how much it has recursed, and we can call that, you know, a depth. We can call it max depth. So we need to define that somewhere. Let's put that just after our other definition. So depth of rays. So you can say var max depth, if I spell it right, equals 3. So we start off with 3, and this recursive ray will assume itself shoots off several other rays and collects all the light color information. Once the maximum depth 3 is all done, it returns to us the final red, green, blue value, and then we just need to plot it, don't we? We're not going to worry about, you know, the lighting factors here. That's going to be done in the recursive ray function. So in some sense, this outer loop is going to be very simple. So all we need to do is say if it's hit, then we choose that color, RGB.X, RGB.Y. Remember, we're using RGB, we're using the P5 vectors, which is just a nice way of packaging up 3 values, and that kind of is quite convenient for red, green, blue. So X, Y and Z are actually the red, green, blue RGB.Z. And that's the color we've picked up from the recursive ray function. And then we fill in that point, which will be at pixel X and pixel Y. And if it didn't hit anything, it missed every object, then we can say stroke, this is the background color, let's say 100, 100, and the final one that depends on how up or down the ray is pointing, ray direction dot y times, I don't know, let's say 1000. That's what we did before. We do the pixel X and pixel Y. So let's draw a picture of what we've just coded. So we have our window, our viewport, we have our camera or eye, we have some objects in our scene, and we're shooting light rays into the scene, and then this is a recursive ray function, so we don't yet have to worry about how it bounces around the scene, but what we can assume is that when it returns a value, it's picked up the colors from here, 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 and we just pick that color, red, green, blue, and color that pixel that's relevant. So the function itself will call itself several times, and it will pick up any contributing colours from the various objects. But as far as we're concerned at this point, we're just working through the pixels on this viewport, and we're just using the colour that's returned by that recursive function. So it's simple for now, but it means we've moved the work from the loop that we had into the recursive ray function. Okay, so let's think about writing a recursive ray function. Now let's create some comments like this, just to kind of separate our code. So we'll keep our sphere object separate from our main code. We'll separate our draw function from the setup function there. And then in here we can write our recursive ray function. So recursive ray. And it takes the camera source, the ray source. And remember, that's only the camera, the light's camera source, the camera position at the start. If it's bouncing around in the scene, then that can be a different position in the scene. What do I mean by that? So the first time we call that recursive ray function, this is the start of the ray. The second time it's called, it might be here, and this is the start of the ray, and then this is the start of the ray, and this is the start of the ray. So it's not always the camera location. So ray source, ray direction, and depth, which we know we set to 3 to start with. So the first thing we do when we have a recursive function is test whether we need to go any further, because we need some way of stopping the recursion. So almost immediately we can say only continue if depth is not if depth is more than, so we're starting at 3, so we want to see if it's more than 0. So if depth is more than 0, we'll carry on working. Then somewhere in here we have to reduce that depth, and we do that when we call the recursive function again. Let's work backwards from this what this function should return. So it should return whether the ray has hit an object, either, yeah, that's right, whether it should hit an object. So we can say intersected as a boolean, yes or no, and we'll set that earlier in the code. It's quite useful to be able to work backwards from what the function should be returning. We also need to return the color that it's collected, and we can call that color contribution. Now, when we start, our color contribution is going to be 0. Contribution. So we can create a triple of 0, 0, 0. So we start off with no color, and then as we recurse and maybe hit other objects, we pick up color contributions, and that will be in here somewhere, and then we return the color contribution that has been kind of collected. So in here we'll need to add to this somehow, and the deeper we go, the more objects we hit as we bounce around, more will be added to this. So it starts off at 0 but gets added to. Now let's think about the intersected. We need to know whether the ray hit anything at all. So we can start that off as var intersected is false, and then if we hit somewhere we can set it to true, and then we can return that. If it didn't hit at all, then we can return that as false, and then we won't we'll just colour in the background, as it were, like we did before. Great, so this is starting to make sense now, it's starting to flesh out. I say sometimes it's hard to think about how to structure a recursive function, so it's worth kind of thinking in the abstract and saying, well, we need always to test when we stop recursing, and that's the counter or depth function. We think about what we're returning and then work backwards from what we need to do in order to get those values right. So we've got an array. Let's say we still have a depth that's more than 0, so we have 3 perhaps, or 2 or 1, and so we need to now test whether we hit an object. And now we can actually copy some of the code that we had before. So we use the nearest point, we test all of the objects in a scene, and if it was intersected, let's do it in bits. So we So we're saying if we have a depth more than 0, we start off our array, we set up some initial variables because we want to see which object is the nearest, so we did that work last time, and we work through all of the objects in the list of objects. Now this list of objects, we can't see that from this function, so we need to declare that as a global variable, list of objects. So that'll need to be outside here. Var list of objects. Let me copy this nice separator just there. Keep that separate. So these are global variables. Global variables. And when we set up our list of objects, we don't need to just set it up as an empty list, and then in our main code we just add to it. But because we declared it outside all the functions, it should now be visible inside our recursive ray function. Great, so we can see that. So we're setting nearest point infinity to start with. We haven't been keeping these variables ready to be used, just like we did last time. We're testing all the objects in that list of objects, the scene. We're saying, did that object hit? We're calculating the distance to the point, and then by the end of this loop, which works through that list of objects, we should have or now have nearest object, and we should have picked up the color from it as well. Great. So now that we've got the color from the nearest object, we need to apply the lighting factors which take into account illumination and so on, that just like we did before. So again, we can cut that paste out, cut that out. But we're only doing that if intersected was true, if we actually hit anything. So if we have hit anything, so if we hit an object, we know the nearest object. So if we're intersected, we can, as before from the previous videos, calculate to what extent the light source is directly or not so directly hitting that point. And remember, we use the normals and the kind of cosine factor. So we end up with a couple of cosine factors to adjust the light. We're clipping it here, yep. Form factor. There's our lighting factor. Great. That's the nearest RGB. We're multiplying it with the lighting factor. We're not colouring in now. Now we need to add this RGB value, the colour that we've adjusted with the lighting factor, to the colour contribution. So we can say add to colour. Can't type. Let's reformat that a little bit. I've got the indent right, yep. Add to colour contribution. So let's add that. Colour contribution equals p5.vector.add colour contribution and then the nearest RGB. Great, so let's talk through what we've done so far. We have sent off a light ray. We've worked out whether it's hit an object, and if that light ray was going to go through more than one object, we've found the nearest one. We've picked up the colour and added it to the colour contribution. We could return that, but actually we've got more depth to go. So we need to set off another ray from that point and collect back the colour contribution from those. So this is the magic bit. This is where the recursion works. We need to work out the bounced ray. So the bounced ray from the intersection point from new source, not from light or camera, not from camera necessarily. Well, it's not from the camera. So we can say var bounced ray equals p5.vector. Now we've worked out how to calculate the bounce ray before, and where did we do? This was the expression we came out with before, and it was this was for the light ray that was bouncing as if it came from the light source. Ours will be analogous but different. We can look at a diagram again, or we can just look at the code and just substitute the variables that are relevant for this bounced ray. So let's copy and paste that. So we're still interested in the nearest normal. Yep, that's right, we've got the nearest normal. That's still relevant. Is it to the light source? We're not using the light source this time as the start of the ray that causes a bounce ray. It's now the ray that came in, the opposite of the ray direction. So let's put that in, minus ray direction. But you know, we can't just say minus ray direction, unfortunately, so we have to do that whole p5.vector.mult ray direction -1, that thing. So this will give us the opposite of the ray direction in the other direction. And the same substitution there. Now if that sounded like we were cheating, let's go and look at the diagram we did last time. Here we were working out this reflected light ray as if it was reflected from the light source. So the reflected light ray was 2 times the dot product of the light ray towards the light source, and the normal, which was scaling up the normal and then substituting the light source vector. So here we just need to, it's the same but with different vectors. So here we've got the ray direction instead of the vector to the light source, so we have minus that. The normal is still the same, so we've using the symmetry in the diagram to come up with a new expression. And then we just normalize it, bounced, as it's always a good idea to assume that our vectors are normalized. And we use that now to fire off recursive ray along bounced direction. So we can say var hit to a different one and a different RGB2 that's collected from the recursive function, recursive ray, remember, which is this function itself. And now we start not from the camera location but from the nearest intersection point, and the ray direction is now the bounced ray. And the depth now we have to reduce by 1, so we started off as 3, now we have to subtract 1 from it. And remember, as this function calls itself, that will get reduced, and we check within the function up here whether it's still more than 0, and if it's not, we stop recursing. Great. And we collect RGB2 to the color contribution. So color contribution equals p5.vector.add, if I can spell that correctly. Color contribution RGB2. So that's what was collected from the ray that we kicked off. Now this one, the colour that comes back from the ray that we've kicked off, I think because it's deeper we should reduce it a little bit so we can scale it down a bit. So we can say RGB, so let's scale colour down because of depth. So we can say RGB2 equals p5.vector and we multiply that by something to do with the depth value. So the depth, so if we say 0.5 times depth, that means when the depth is high, this value is fairly high. As the depth gets smaller, because we've got further into the scene, the number gets smaller, which means the contribution gets smaller. That makes sense. Contribute color. Now this should now give us a scene that works. Let's try it. I suspect there'll be some typo, some error. It always is. I think it's just extremely lucky when we can write code and then run it without any error. Ooh, okay, camera location not defined. Line 121. So that's inside this recursive function. It doesn't know where that camera location is. So let's make that a global variable as well. var camera, oops. Let's try that now. Light location 142. Yep, that needs to be of global as well. Var light location. It makes sense that those information, those variables related to the scene, are visible within that recursive ray function. But before I look at this error, I'm not sure about the camera location, whether that should be global. Yeah, I've made an error there. That should be ray source. Yeah, that should not be in a global, so I'll undo that. The camera location doesn't need to be global. That's just the starting point for a ray. That's passed as a parameter to the function. Right, let's start that again. Let's see that error again. Great. Camera lock is not defined, 127. We shouldn't be using that in the code. It should be the ray source. It's a good way of debugging this, isn't it? Okay. So something's happened there, but it doesn't look right, so we'll have to debug that. It's interesting that we are getting some kind of bouncing visibility of colours in one object that come from other objects, so something is looking encouraging, but we've got to debug some error here. So this thing that's popped up here is Open Processing's way of detecting whether we've written code that's just going to run forever if we've accidentally done it. If we add this no protect comment at the top of our code, then it will disable that protection. So we can say no protect at the top. Right, let's now try and debug where that error came from. So I'm looking again at this quite long bit of code. We can simplify some of that work by saying, instead of subtracting, we can add not the negative of the ray, but the ray direction itself. So that will just reduce some of the calculation a little bit. So one way to debug these recursive functions is to simplify things by actually reducing the depth. So we'll start off with 1, and that should just give us a scene as if there was no reflections. Right, so something that sticks out is that this scene is upside down, and that means we need to we forgot to do 600 minus the pixel Y values. That should turn that upside down. Otherwise the scene looked fairly correct when we had depth of just 1. Okay, so that's encouraging. So now let's look at depth 2. Okay, so it seems to be partially correct where, say, in this blue sphere we are seeing a reflection of the green sphere, and the same with this pink sphere, we're seeing a reflection of the green, and in the green one we're seeing a reflection of the pink one, but the shading doesn't look right. Great, I think I found the error. It was quite a tricky one. So let's look at a diagram to explain it. So when we bounce a ray, after the first kind of intersection, and we're testing for the next intersection. And previously we just tested to see whether, if there were two kind of points here, 1, 2, we wanted the smallest value of t to get the nearest intersection, so entering an object, not exiting it. But actually t can be negative. We could be going backwards, and we don't want that. We only want t to be going forwards. So this is the ray direction, and solving the equations for intersection, you can get a negative t for backwards. We don't want that. So we just need to include a test to ensure that only intersections where t is more than 0 are returned. So we go to our object definition, our sphere, and here we've worked out t to work out the intersection point. Actually, we can just add in a little check to see ensure t positive for forward ray direction. So if t is less than 0, we can say actually it didn't hit. So we can say delta is false or -1. So if it's -1, then that's as if it didn't hit. Is there a more efficient way to do this? We are calculating things here, perhaps unnecessarily. Oh, that's fine. It's a simple code for now. We can optimize it later. Let's see if that makes a difference. Great. That's much better, isn't it? That finally worked. So we have a blue sphere here, and in it we can see the other spheres reflected. We can see a yellow reflection of the yellow sphere. We can see a reflection of the green one and a bit of the red one as well. We can in the pink one we can see the blue one reflected just there, green one there, yellow one there. So this is quite good actually. This is and kind of an idea that's relatively simple in terms of how we talked about the rays bouncing around in the scene, and yet when we've coded it up, it's actually quite sort of impressive that it works as well as it does. I think that's quite nice. I think I'm going to see if I can make these objects a bit lighter because they are quite dark. Okay, I'm gonna see if I can fiddle with this lighting factor a little bit and see if I can lift up the light levels. So at the moment we're just multiplying two numbers which are from 0 to 1, and multiplying two fractions makes them even smaller. So I can make sure that there's a minimum by adding 1.1 plus that factor, and I can scale that so that it is still in the range. So if this could maximally be 1, so this could be 1.1. So what I can do here is divide by 1.1. So this will go from, originally this was from 0 to 1, now we'll go from 0.1 to 1. Let's see if that kind of lifts the lighting a little bit in the scene. Great, that is much better. I'm quite happy with that now. I'll make a save just to save that code. That's fantastic. That is really good. Now what we can see here is there are obviously reflections of objects in other objects, and the depth of 3 is giving some almost surreal results where we can see objects reflected back into themselves. What I want to do now is address something that's quite important that we kind of overlooked. So let's draw some pictures to kind of talk about it. And that's this idea of shadows. At the moment we've assumed no object casts a shadow onto any other object. But actually we should think about how shadows work. So let's follow this light ray again from the camera or the eye onto the scene. If it hits an object, we create another ray from there, our recursive ray. But actually, if this point is in shadow, we shouldn't. We just we sort of say, actually, there's no contribution to the colour if this is in shadow. And the way we test that is if the bounced light, the bounced ray from here to the light source has an object in between. If there is an object in between, if there's a hit along this ray, then we can say nope, we don't contribute anymore to the kind of the continued contribution that we recurse. So let's go back to our recursive ray function and think through the logic of how that works. So we start off our ray. We've got the ray source and the ray direction. We're checking that the depth allows us to carry on. Great. We work through our list of objects to see if any of them intersected. Yep. And we've got the nearest one. Now, this is where we check. So, yes, we've checked to see if an object was hit, and now we've got the nearest one because we've worked through that. We just need to work out we've got the light source there, we've got the vector to the light source, so that's useful, we need that first. And then we say check if in shadow. So we can say var in shadow. That can be a boolean. Start off with false. And we go through all the objects again. So we say for var object in list of objects. And we say as long as that object, we must exclude ourselves, so if exclude, want to exclude the nearest object, so exclude the nearest object. So if object doesn't equal nearest object, then we check for intersection along reflected ray. So we can use the intersection function of the sphere objects, just like before. So var hit, call that temporary hit, and RGB temporary equals object dot intersection nearest intersection point is where we're starting from, but this time heading in the direction of to light source. So it's from here heading in the direction of to light source. We're testing all the objects in the scene except the current one to see if there's an intersection. If we did hit, if hit temporary, we update the in shadow boolean true. So there might be several, but if at least one hits, then we know we're in shadow. Great. So that means we know we're in shadow. How do we use that value? So we have two options actually. So let's draw a picture here just to show. So here's one object, here's another object, and here's the light source. And we're following our ray. Imagine it hits there, and then we test this point to see if it's in shadow by checking the bounced ray towards the light source, and we can see that it hits another object. That means this point is in the shadow of this object. Now we could just say, okay, if that's the case, we return black. There is no contribution, it's just harsh black. That's one option. and that's entirely valid. In fact, it's probably the correct approach. Another option, because we're allowed to be a bit creative here, is to say actually we will return the color here, but we won't create any more bounced rays. So that means we should still be able to see this color even though it's in shadow, but it won't have any other color contribution to it. So that might create an interesting effect. So let's try that. So here we can do that with the lighting factor. We can say if in shadow half the lighting factor. So if in shadow, so we're allowed to kind of bend the rules of physics just a little bit, right? Just as we did here, really. We're simulating the effect of ambient light a little bit. Lighting factor is 0.5. We can just say times equals 0.5. So we've halved it. Great. So that's we've halved the lighting factor to make that point that's in shadow a bit darker, and then we can decide whether we bounce any new ray. We can say only if not in shadow. So if not in shadow, there, that whole section of code there will only be done if we're not in shadow. So we're gonna only kick off a new ray, collect the color contribution and add it to our contribution if we're not in shadow. Let's see the effect that has. Hopefully we'll be able to see some shadows. Oops, there's a bit of a typo, line 110, nearest object. So we're not talking about the nearest object. What are we talking about? Yeah, we do want the nearest object, but we didn't collect it. So where do we define that? Yep, when we find the nearest object, we update it here. Nearest object equals object, but then we need to declare that variable further up here. We can do that there, var nearest object. Let's try that again. Another typo, 114. The intersection function returns 1, 2, 3, 4 things. So hit temporary, intersection point, temporary, normal, temporary. We're just calling those temporary because we're not going to use them. Let's try that again. I found the error. It should be of, not in. If I do in, it gives me an index. If I give of, it gives me the objects. It's a common error. Let's try that again. Great, that's fantastic. So you can see a shadow here. That shadow has been cast by this ball. In fact, I strategically placed that ball there in order to do that. So that works. So the light source is up here to the right and up, and it's this pink ball is casting this shadow just there on the yellow sphere. So that's fantastic. That shadows work. Brilliant. So that's all the bulk of the work done. Let's do a couple of fun refinements. What should we do next? We could look at adding some texture to the spheres. Now, texture can be added in many ways. It's actually quite a simple thing to do because all we're doing is changing the returned color. There are lots of ways of doing that, and a particularly simple way is using the noise function. And again, do go back and look at the earlier tutorial videos on noise, perlin noise, because it's very effective and has lots of uses, really worth knowing about. So for us, the code change is really simple. We go all the way down to our sphere object, which returns the color of the sphere, and all we need to do actually is somehow adjust that by noise. So let's write in, let's write some comment, texture the color. So we want to return, let's call it RGB2. So var RGB2 equals something to do with the original color, this .rgb, and we want to maybe adjust it by noise. How do we do that? Well, we need to use the p5 vector function dot mult. So that takes that vector, this .rgb, and multiplies it by a scalar value which we need to work out. So we could say it's noise that depends on the position, or maybe the normal at that point. So maybe it's normal.x, normal.y, and maybe even normal.z. But because those are quite small, we might have to adjust things a little bit. So maybe multiply those by 5 to make them a little bit bigger, those components of the normal. And because noise goes from 0 to 1, let's maybe multiply that by 2. Let's see the effect that has. So we're just mixing in a bit of perlin noise to the RGB value. Ooh, I've made an error there. It's not this to RGB2, it's just RGB2. Great, look at that, isn't that amazing? So we've got spheres here, and the surface colour has now been kind of perturbed a bit by noise. And you can have a play with that yourselves. You can use other mathematical functions to create stripes or kind of wood textures like we've done before, or maybe checkerboard type functions. You know, you can use your imagination to kind of come up with any kind of function that adjusts the colour or even defines the colour. So that's really simple in some sense, but it's quite effective when those textures, those mathematical functions, are wrapped around these spherical objects. So that's really nice and effective. I'm quite pleased with that. Just one more thing we can do, and it shows the power of mathematical modelling of scenes, is we can use code to create lots of objects. So we've created some 1, 2, 3, 4, 5 objects here, but we can just use a loop to randomly create a scene. So we could say var I equals 0, I is less than, I don't know, 20, to make 20 objects. And we can say we can invent some kind of color. We can say x comma y comma z equals another list which happens to be random from say -10 for the x to +10. That's the first variable, which is x. Another one would be y, which can go from -10 to 5, not too high. And then z, the depth, that can go from -10 to 10. You can always adjust these later. That creates x, y, z at random values, constrained a little bit. We can create a random diameter, var diam equals random. We don't want it too small, so maybe starting off at 0.5 all the way up to say 3. We can create a random RGB, create vector and random 255. We can pick all RGB, but all of them to be random, like that. Copy and paste that, and then we just add an object to the list of objects. Dot push, new sphere, and the sphere has x, y, z as initializing values, a diameter, and the RGB value. So let's see what effect that has. That should create a random scene. Fantastic, look at that. That's created quite an interesting kind of set of blobs, and there's certainly lots of reflections going on there and some shadows being cast there. I'm really pleased that we didn't make them entirely black, but did allow some light to come through just to create a darkened area so we could still see the texture on the objects. Let's run that again one more time. Again, fantastic. They're a bit low, so I'm going to adjust the random range from, say, -5 up to 10. Try that again. Fantastic. That's much more balanced, isn't it? Well, that's pretty cool. And you can, write your own code to add many more objects. Obviously, the more objects there are, the longer the calculations take. But this is pretty impressive, isn't it? For not too much code, a bit of code. Relatively simple ideas, which we've talked through over the last few videos. We've managed to create ray trace scenes where we are following light, reflecting them, spotting shadows, seeing objects inside other objects. I mean, look at that one. It's amazing. We can see almost the entire scene in that blue sphere, and another one there. I think that's amazing. These objects have kind of merged together, so that's interesting, and that's fine. And you can see almost the highlight there as light bounces back and forth between the two objects. Yeah, and we've managed to do a bit of texturing in a very simple way just to show that it's possible. So I think that's really fantastic. I think that's amazing. Have a go yourselves. Just to leave a finishing thought, and you might be wondering why we've only used spheres. Well, spheres are actually really easy mathematically. We might not have thought that, but the maths works out really easily in terms of working out whether a ray intersects a sphere. The maths is really simple. But let's talk a little bit about how we might model other kinds of shapes like cubes or spheres. So let's look at this picture. So we've got a light source, and well, it's not a light source. We're working backwards from the camera or the eye. We're shooting a ray into the scene, and in order to calculate how much light there is, in order to do the shading, and in order to also bounce a new ray off that object as a recursive ray, we need to know a few things. We need to know how to calculate the intersection. We need to know how to calculate the norm that sticks out of the object, and the material color. Now, the material color is really easy. We can either be constant, like red, green, blue, or it can be textured in some way using a mathematical function, and we've seen how to do that. The norm and the intersection are the things that we need to be able to work out. So if it's a flat plane or a cube or some other object, those are the things we need to be able to work out. So once we've expressed it like this can be any object, a sphere, a cone, a tube, a torus, as long as we can work out these three things. Anyway, that's the end of that series. It's been a lot of work. Well done. Hope you've enjoyed it, and do have a play yourselves. This has been in JavaScript. The links that I'll include in the description also point to Python if you're interested. Have a go yourselves. Bye.